Hey, welcome to the last lecture. As I told you on the Discord, you will notice two behavioral changes from my side today. One is that I'm not be able to get up and show you the board there. The other is after an elephant stepped on my foot, I was prescribed some opioid. So if I smile a little bit more, that is the reason. So the lecture most likely will also not last for 2 hours and 20 minutes, as typically lasting. But I will stop around whenever I am able to stop and spend the last few moments spending some time on next steps for you. Some kind of guidance as to what we left on the table, because obviously this is an introductory course. What potentially you could be busy building on your own during the summer, if that's what you want to do, of course. But I want to start today with the imminent deadline of the project, which is following the typical pattern. Judging from the tickets, there is a lot of panic and a lot of confusion as to what we are delivering, as if we didn't have a month to discuss all that. But nevertheless, what we are delivering is definitely the code. Make sure that on Sunday you deliver a repository that can be seen by the TA. If you are in any doubt, look at the repository you were submitting in your assignments. Make sure you add the TA properly as a collaborator. Do not open ticket. Can you please check if you can see it? Do not open it. These tickets will be immediately deleted. In the next iteration of the course, we will have an agent automatically deleting the tickets. Right now, we are deleting it manually. Okay? You are capable of checking that your assets are accessible. In terms of code, do not commit large files into any GitHub repository. Link them via a storage facility. Like you want to deliver the video, right? You, as we mentioned, link it, upload it into your G Drive, make sure it is accessible again by either the TA or anyone with a YouTube email, with the NYU email address, and link it in your README file. If you are submitting as part of teams, make sure all the team members both team members are listed with both names and email addresses. In the very beginning of the README file, you need to submit, both of you need to submit the URL where the GitHub repository is located. Okay. Anything else? I forgot. Okay. Of course, we are going to be grading based on three things. Obviously, the performance. If the interviewee sounds like a whale, then most likely it will be like Nemo. Seen the Nemo, the movie? Yeah. If it sounds like, was it Nemo the one that was doing that? Or some other actor over there was sounding like a whale? Or maybe a whale was there. I have no idea. I can't remember. But if it sounds like this, as originally was given the project sounded like this, right? If you listen to the Hormuz, Strait of Hormuz initial kind of voice, then the performance will be judged very poor. But if it is better, you'll get points, obviously. The second thing is coverage. Has all the tasks been covered? All the stages of the pipeline? Is there a solution there present, right, or not? The best guarantee that the TA, which is under a lot of stress, because they are students, they are coming, they are facing deadlines themselves, right? Will be able to find your solution is to include it in your README file. Mention it, what things, and this is the third thing we are judging, documentation. Like face problems you face. Hey, I never had a GPU. I did have to use a Colab. This created some issues, blah, blah, and so on. Even if something didn't go as planned, code it. Maybe you are lucky and the TA assigns you some points because of that effort. So if you submit just a single URL, as in everything, right, then it's impersonal. How can I say that better? I think you get the idea, right? So you're trying to deliver your work in the best possible light. So put some effort there and make sure that everything goes smoothly. Second thing is about the final exam. On Wednesday, I'm going to post your topics, okay, in Discord. Make sure that if this thing improves, I will be here. But if it doesn't, oh, sorry, what am I saying? My plan is I will be in Boston on Friday. If this thing improves and I can walk the dog, because I have an apartment in Boston, I have to go down, walk the dog, and go up again. Okay, so if not, if it doesn't improve, I will be in New Jersey. I cannot be here. I'm sorry, but I will be here to present it. Okay? The TAs will have the solutions in front of them, as it happened also in the midterm. They will be able to guide you throughout the exam if there are questions. But I typically write now these exams with a lot of text, so you don't have to ask questions. All right, that's it as far as logistics is concerned. 2 items to go through, and then the nightmare will be over. All right, so we will then move on to what we will do today. Let's move on to what we will do today. So today, the plan is still to go through the reinforcement learning. Obviously, there are sections here in this page that I'm not going through in this course. Okay, so not everything will be covered. I will stop. I will cover the basic reinforce, the policy-based kind of gradient policy gradient methods, and then I will stop and then switch to the last 15 minutes to give you things that you may want to study, okay, during the summer. Okay. Before we start, let's review briefly what we covered last week. Okay, so last week we were still on the topic of Markov decision processes, and we started introducing the objective function. Okay, after going through a whole bunch of definitions, the return was quoted. We wrote actually down the state value function, which is obviously as a function, is a function of the state. And this means that for every single state, I need to have a scalar value associated with it. How we estimate these values was the topic of the Bellman expectation equation, and which gives us this kind of recursion. And also provide together with it a tree that we're able to use in order to understand visually what is going on. How the value at this kind of state that I'm starting now at time kind of t will move because of two random sources of randomness. The first source of randomness is what? The very first, as you can see in the diagram. The first source of randomness is what? State. The policy, the pi. Okay, the policy itself may be stochastic. It is actually sometimes better to be stochastic than to be deterministic. So typically we are dealing with stochastic policies. The second is the state transition, the PSS pi. Two sources of randomness, right, are involved, and therefore, when we see an expectation over there, right, we are saying expectation under policy pi, which is itself stochastic, and inside this sort of brackets, parentheses of this kind of expectation, the expression of the expectation, we see the reward, which is of course a random variable. And obviously the S prime, which is the ST plus 1, which is yet another random variable. During the development of this thing, it pays to be formal. during the development of your understanding in reinforcement learning. It pays to be formal in what sense? I was not that formal in the, I will call it what I was writing, in the sense that sometimes you see here v pi of s prime, right? S prime was the value of that, but inside that it was st plus 1 is equal to s prime. Okay, so with capital letters, you understand immediately when you have an expectation, a lot of capital letters are random variables, right? It's only when you replace the expectation with summations, because you know the probability distribution, only then you are entitled to write the specific values, right? The small letters, if you like, the action, the reward that you actually got, and the S prime you ended out. All right. By passing that, we looked at the prediction example. Okay. I think it was straightforward using the grid word. I think sticking to a small grid word initially for you and going through the Python code that later on showed up, actually even here it showed up on the website, is the best way to understand what's happening. There was a notebook that we went through and did the expansion in various depths, depth 1, depth 3. It is there for you to understand how the estimation is done. The notebook, of course, it's here. Make sure you go through this notebook, not here, but here in the MDP. Come on. Did I not press it? The website went down. For you? Oh. Oh, no, I don't believe this, really.
No, it's not. No, it's
up.
You should reconnect Wi-Fi. Volumes.
Okay. It is here. Single suite, not single suite. Wait a second, this is. Yeah, this is the one. This is one. Okay. Make sure you understand for the MDP what's really happening. Okay. So, don't have line by line. Finally, we realized that this is a system of linear equations. We solved it. Okay. We went through a two-state kind of problem, and we solved it with what is called the iterative policy evaluation. Okay. If you understand the two-state solution, you understand the n-state solution, you're in good shape. So this was basically the equation. It was part of yet another kind of notebook that shows how this effectively converges to the AX is equal to B with NP libraries usage, right? Which is not recommended. Then we looked at actions. Actions are more, the action values are more informative than the state values. Why? Why the action values are more informative than the state value? Because if you know the Q values, as we call them, right, you can always move easily in a greedy way, right, and pick up this action immediately. You don't have to assume that this specific, I mean, remember the value, the state value is an average. But if you have the Q value, which was the state and the action, is far more immediate. That's why it's called more. That's why I called it more informative as a quantity. Obviously, it requires more stuff to compute it, right? Obviously, because it has the action or the composition there. But it is, luckily for us, also computable via yet another Bellman expectation operator. The key thing in both of these kind of operators is the fact that they are contractions. And the very fact that they are contractions allows us to find ultimately even in the case when we are looking for the pi star, right? Not just evaluation, but we are looking to find the pi star, the optimal kind of policy, to use iterative schemes that we went after that discussion. Okay? And these iterative schemes were based on the two Bellman optimality equations that were effectively called the V star equation and the Q star equation. Two equations were there, and we went through a robotic example just from the V star kind of perspective, which was easier. The recycling robot example was, I think, it was pretty straightforward. We wrote down the two equations, the V star of L and the V star of H, the high and low state of the battery of the robot. So you should be very well versed into translating an English problem statement to an equation, to an update equation. And most of the examples here in the website and also some of the examples that you will find in the Satons's kind of book are also guiding you through that. Then we looked at the the policy iteration and value iteration. And we have looked at policy iteration. We looked at policy iteration as a two-stage solution. Okay, the two-stage solution that involves first the policy evaluation, just like the set of linear equations that we did it earlier, and then the policy improvement was basically the heuristic. Right? We are effectively involved the greedy heuristic here, and later on today we will see how this greedy heuristic can become what we call an epsilon greedy heuristic, which we will follow with some probability. This helps us with something that we'll see in reinforcement learning, not in. So we saw this specific example over here, which I really advise you to look at as step by step. I didn't go line by line through the manual derivation, right, of this problem, but I gave you a grid word, and I asked you, okay, apply on that grid word the policy iteration scheme in order to find the pi star. In other words, for each and every square, I want to see an arrow. That arrow was gradually estimated first with the proper policy evaluation. The policy evaluation iterations need to complete. And then with the policy improvement was the greedy policy that ultimately will result into the pi star. How and when do we detect that we have a pi star? Because of the contraction, we are detecting it when the policy does not change. Mind you, the value may continue to change. The values may continue to change in the problem, but the policy isn't because of this greedy heuristic. Okay. Whether I have 20 or 22 does not really matter if 20 and 22, either of them is the maximum possible value for that state. That is the intuition behind it. It's very easy to understand. So so you can go through step by step in the kind of a notebook which is called Policy Iteration Grid World, and I hope you are doing that and you arrive at the solution. Put some print statements there to understand what's happening. This stuff is kind of easy, but because everything is like a mountain, people are not doing the whole thing, and they don't understand fully what's happening, and then it's like a domino effect after a while, and then it becomes like, oh, whatever. I will just use a library anyway. That's fine. You can use a library, but during the interview for the companies which is working for, they want to see that you are also understanding what is behind the library. Okay. Value iteration was entirely based on the observation we did kind of earlier. And the observation we did earlier was that, hey, if the policy is there early, without really waiting for the policy evaluation to happen, right? Can I just take any value function and do the greedy part. So I can start with one sweep, get a value function, take the greedy kind of approach. Then I will be able, without, in other words, reaching the line with the policy evaluation, remember this V thing that was converging, I was able to do effectively hill climbing on the whatever value function is happening in every step. That pi prime that I obtained in the first greedy thing, you can actually update the value, do another one and another one. So it is a, I will call it a shortcut. However, it simplifies a lot in the computations because you don't have to go into multiple for loops for the policy to be evaluated. The second kind of notebook was there to be able to give you the sort of same solution for the value iteration. So it's for these specific notebooks, for this specific problem, sorry, grid work, either you use policy iteration or value iteration, just doesn't know. You need to be familiar mostly with the, not for the exam I'm talking about, I'm talking out there, value iteration is what most people are doing in order for them to get into a solution, which is anyway, ultimately, for most practical problems will be approximate. Okay, because MTPs, as I told you, they are there, quite widespread. The kind of many problems are solved with MTPs. I mentioned, I think, in this class or some other class, I can't remember now, the hotel reservations, the airline sort of ticket purchases, all of them are gigantic MTP problems that these vendors, the airlines, hotels, are solving to get you to pay more. So you will see some this discussion. I had this type of discussions in my website. I deleted it because there was not a lot of. Anyway, so I want to go now to reinforcement learning. After this kind of notebooks, this is plenty for MTP. There are some others over there has examples, much smaller examples on the grid world you can actually see. And I want to start. This is lecture. Let me. Today we have 1st of May. In lecture 13. Lecture 13. So the topic here is reinforcement learning. I want to provide some kind of a taxonomy of various reinforcement learning algorithms and what we will limit our discussion today. The first one is the so-called value-based schemes. And one of them is going to be called SARSA. The other is going to be called learning. The other one, the other kind of category is going to be called policy-based. And finally, this is where we conclude. Reinforce. This is the mother of many today's modern kind of reinforcement learning algorithm. And the other category is model-based. Monte Carlo. And this is research algorithm, such as the one that, Monte Carlo research is foundation, but some hybridization of many schemes kind of led the ones that you are familiar with, or you're not, you're listening in the news. So what you're listening in the news are hybrid algorithms, like, for example, they borrow ideas from both policy and value to create algorithms such as PPO, OpenAI, and some degree, some approximation of that, mostly policy based, I would say, is the so-called GRPO. So PPO stands for proximal policy optimization. And this one stands for group relative policy optimization. This one was put in the news mostly from DeepSeek, but it pre-existed earlier. Some degree. Another scheme like to zero, which is well known from earlier kind of attempt from the Google DeepMind kind of team to solve the game of Go. This is the category of algorithms that are there. And there are some others which are not strictly speaking reinforcement learning, but you're hearing the news like the DPO or direct preference optimization, direct. So this is another island, I would say. Outside of the pure reinforcement learning space, despite the fact that it's giving you a signal to not policy, but preference. Not policy, preference. This is not policy, preference. This is basically what you see when you are presented with two options. Choose one or two, but the ChatGPT is giving you these two options. You know, I prefer one. Therefore, that preference goes somewhere. So, that's the policy. Okay, so what we are going to start our discussion first is the sort of value-based methods. I forgot actually to mention some. When we deal with each one of them, there was some kind of background. Like, for example, right now I'm going to start the value kind of based methods, and I'm going to start with the foundation of those, which is the Monte Carlo approach. So, number one, Monte Carlo prediction. Just like what I did with MDP, I'm going to split the discussion into two parts, two subparts for each kind of scheme. One is the prediction problem, and the other is the control problem. Remember, in MDP, we were dealing with policy evaluation. This was the prediction problem. And then we said, oh, apply heuristic like the greedy, that was the control problem. So we will be following similar kind of pattern here. Monte Carlo prediction. All right, so in Monte Carlo, oh, by the way, I wanted to also show you before I get started. where we were coming from, I think I showed you this picture before. We're coming from MDP now with all the knowledge that we needed. We were having all the knowledge of the conditional probability distribution, P of R comma S prime, given S comma A. This is the MDP dynamics. Given that we're coming from S and the action A, what reward and S prime you receive, give me the probability distribution of that. And because we knew this kind of probability distribution, we are able to easily replace the expectation with a summation. Because when you replace the expectation of the summation, what is the first thing that you need? The probability distribution. I mean, the expected value of X, again, from the elementary school, expected value of X is equal to what? Summation X, P of X, right? So if you don't know the P of X, how are you going to expand the expectation? How are you going to calculate the expectations, right? So this is what I meant earlier, that, hey, a lot of these things are possible because of our knowledge of the MDP dynamics. As a result of that, we could expand for all possible actions, right, that we can take, right? Therefore, we knew the sort of, we can sample out of the random policy that we have, stochastic policy. We were hitting all the possible kind of actions you see here with the black circles, the solid circles. And this led us via the knowledge of the PSS prime, because we knew the MDP dynamics, into a whole bunch of new states. This is the depth one expansion, which I told you it's in the notebook. And each of these kind of states has a value which themselves were defined from what? From another expansion, right? And from another expansion, at some point, some of these expansions will lead to some terminating kind of states, and some others may continue forever. Okay? But at the end of the day, even if they continue forever, the value, right, because of the discounting, is going to convert somewhere. Therefore, you can backpropagate everything and come up with the expectation at the ST where you started. Now imagine this happening for all states. That's how you end up with the evaluation of the policy. That's what will happen inside the four loops that I mentioned that you need to go through to understand how the expectation is implemented. Now, over here, we are obviously, definitely dynamic programming is an improvement compared to exhaustive search. Because I can try exhaustively and find the best possible thing I can do, which is, of course, mission impossible for any practical problem. We went to dynamic programming with a policy iteration and value iteration to make our life easier and more sort of computable. But because of right now, we don't have the MDP dynamics as a knowledge, right? The only thing we can do is to go around and create trajectories until we terminate. Only we terminate, we can actually see exactly, compute exactly the summation of all the returns we got from the moment I started here until I moved in some random trajectory in this room and exited the door. That is my termination state. I can go, I'm storing everything as I'm observing them. Now we have observations, right, of actual returns that happened. And therefore, I'm able to estimate the value. Okay, so I will do that. Okay, so this is now depth first. Cannot do anything other than go in depth first. We'll see now potentially some improvement on that we can do, which is called temporal difference, and implements the approach of learn as I go, which is going to present in some kind of intuitive way so that we can understand it. But right now we are in the let's go and terminate. As you can see, there are some issues with let's go and terminate. They are not practical. It's not practical in many programs. So I'm drawing over here. I'm starting from some kind of state S. And as you know, I'm expanding. I have a policy which allows me to select for any possible set of actions A. And for some action A that I am finally committing to, I'm going to be leading myself into another state S prime. And I'm going to have another action, sample from my policy, and go to another S double prime. And sooner or later, or maybe I will reach the terminating state. Now, this thing here is the trajectory tau. We know that ideally we want to implement this kind of expectation. GT is a random variable, right? And now we must have to compute the expectation what? Just to make sure everyone follows what I said 2 minutes ago. In order to compute an expectation, we need the probability density function of probability distribution of the random variable. What is the random variable here? GT. GT is the random variable, the return. Okay, so we know, however, that the GT is equal to summation from K is equal to T plus 1 to capital T, which is our duration of the until we reach the terminating state, right? Our the time until we reach the terminating state, gamma K minus T plus 1 RK, where RK is whatever random sort of this is T, and this is T plus 1, right? This is basically RT plus 1. We have an RT plus 2. We have all of this, whatever reward the environment will send us. Okay? No surprises with respect to this summation. This is the definition of the return that we did it when we looked at MTP. Go back to your note and see how we defined the return. Right? The return was, what is the return? No, it was here. It was here. Do you see the return as a definition? Right? GT, the return at time t, is a discounted summation of all future rewards. Okay, so we have the discount factors. And here, because we terminated, we have the summation over t, right? From the moment t plus 1 until t, capital T. And what we will do now is we will attempt to perform something extremely familiar to us. We saw it for the first time when we looked at hidden Markov models, and something similar will happen here. Remember the drone localization problem? And in the drone localization problem, I was doing first I was answering the question, what was the location of the drone if we receive successive measurements, C1, C2, etc., and I gave you the Gaussian assumption there for the measurements. If you remember that kind of discussion, right, this kind of question at least, you will realize that something similar is going to happen here as an expression. So when it comes now to the return. So I'm writing that in order to estimate the returns, we want to establish a method where we update the return kind of estimate every time we get a new return, right? Every time we get a new return. And also we want to update the estimate not only every time we get a new return, but over multiple trajectories, because over here we will be generating many trajectories. Some trajectories will go the S prime state, some others will not, but maybe many trajectories will be involved into hitting in quotes, a state. Okay, so as I'm trying to exit the room, I may go over there and turn left to exit the room, but I may go over here, over there, and go straight to exit the room. I will go through that state anyway, okay, 2 times. Okay, so what are the number of times that we are getting through the state? We'll need to designate it as a number, right, a counter, and then see how that estimate of the return will actually be affected by that. So for each time step t that S is visited in an episode, increment the center, there's the counter, N of S. That is the counter of visitations of the state S. Calculate the total return, G T of S is equal to GT of S plus DT. No surprise that this is the total return, because I know I can see the definition of the GT with small letter t. At the specific time that I'm visiting state S, I have some rewards to be won, rewards to go until I exit the room, and therefore I will be incrementing this counter, and I will be summing all the returns from that state that I hit. Right? Are you following? So number 2. Yeah.
What is the superscript?
T is the time t. You remember? You see, is this t? I'm now designating the time. I'm in a state at time t, right? And I'm looking at my future.
So,
Just like earlier in MDP, I was in some kind of state and I was looking at an expectation. And I wrote down the expression that will allow me to calculate that kind of expectation. I'm now going to be writing the expression that will allow me to calculate some approximation on that value. At the end of thousands of episodes, P pi of S is equal to GT of S divided by N of S. And this is V. Remember, I was telling you about the notation that you need to be formal a little bit because you may be lost because of notational deficits. Now, this capital V is an estimate. Small letter v was associated with MDP problems where we knew the everything and we could calculate the expectation. Now we are approximating the value, and this approximation is the capital V. Capital V and small letter v in Saturn's notation are 2 different things. One, the small letter v is expectation and knows the knowledge of MDP dynamics. Capital V does not, is in reinforcement learning, but does not know the MDP dynamics. And the only thing we can do is we start counting. How much return did I get in this episode? If I hit the same state again, how much return got I in the second episode? If I hit the same thing again in the third episode, add that too, right? Over many episodes, as n goes to infinity, this one will approximate the small letter v by this. Following what's happening. So effectively you have, let's say, some state S, and this state S is being hit from thousands of trajectories that may start from different states, right? Because of the stochasticity of the environment, right? And the stochasticity of the policy. I may start from the same state. In fact, I may go into some divergent paths, but yes, I'm going to hit the same state S. And the expression is valid for that specific state S that I'm hitting multiple times. How many times? N of S times. If someone asks you, what is the maximum likelihood estimate, the best maximum likelihood estimate, as we already saw it in lecture number 3 of Gaussian P model, right? You told me that is a sample mean. What is a sample mean? This thing. The sample mean. You told me that the new star of a Gaussian P model is x1 plus x2 plus x3 blah 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 divided by capital N, right? The N is the number of data points I gave you. So the best possible expectation, right, approximation to an expectation is some form of counting these returns now. Right? So now we will do something that will connect that to the expression, the same expression we saw earlier in the Kalman filter discussion. I want to spend some time on describing what is called the incremental mean approximation. That will allow me very easily to do the following. I have an estimate, capital V, pi of S. And I'm now at episode 1000. When I get a new episode, 1001, how do I update the V pi of S? Do I start from the beginning again, counting? No. The incremental mean approximation was also used in the Kalman filter discussion in that drawn example. Going back several months ago, it looked like a year. Okay, here it is. And I gave you this kind of problem that the drone was somewhere and I was trying to find it. Okay. And I wanted to get the best possible maximum likelihood estimate of its location. And I gave you that a measurement model that related its location, the x of t, right, with the z of t. Here, this expression, effectively making the z of t a Gaussian random variable with mean mu of t. HMM is in scope for the final exam, by the way. So, do you see what we did? We started with a maximum likelihood expression of what is the mean of a Gaussian random variable. That is a sample mean. Do you recognize inside the white square bracket the sample mean expression? Yes, you must recognize it. Okay? If this is the expression, look where it led us. It led us to some incremental way of updating that mean, right, from the new measurement as the measurements are coming in sequentially, right? So the magenta expression had this format. The new mean is the old mean plus some scalar times some difference. We will see the same expression now for updating now the returns that we will get, right? Sample returns. We are updating sample returns. I hope the two are a little bit closer. Incremental mean approximation. We know that just now we showed that mu k is equal to mu k plus 1 minus, plus 1 over k of xk minus mu k. This is what we have just looked at in the Kalman filter. We just converted our discussion over here. In fact, if you don't understand this straight away, remember mu k, what is mu k is 1 over k summation from j is equal to k of xj. And this one can be written as 1 over k of summation from j is equal to 1 to k minus 1 xj plus xk, which is effectively this. Okay, so this is no. Okay. Incremental mean approximation, that expression is no. So effectively, what we are going to do, we will adopt this and we will write now the running sample mean. So I am having here the expression V pi, capital V again, V pi, yes, is equal to V pi, V pi, yes, plus alpha GT minus V pi of S, where alpha is 1 over ms, and this is less than 1. This expression governs for every state the value prediction. Right? We are updating the new value after we get a new sample return to go for what is to be here. What is the value of being here? Oh, maybe 100 trajectories, we never see the state again, right? We will not update. This value will stay as is. But after 100 trajectories, the 101 trajectory happens to visit that state. We now have the expression to update the value. That's all it is. The moment we have the 101 trajectory, we increment the ns to ns plus 1, and we will plug it into that expression, which is basically the running sample return from that state S. Effectively, the approximation to our value function on that state. A new scalar is updated. Okay. That is basically Monte Carlo prediction, nothing dramatically intelligent. Really. I mean, there's no intelligence, just counting. So, one thing that it is quite sort of important to write down, we always can remember it, is that all of these are possible because I terminated. Only then I know I can go back and say, oh, I have a memory of all these kind of returns. Let me calculate the GT for that specific trajectory. So let me write it down. In Monte Carlo prediction, the capital V pi of S can only be updated at the end each trajectory where we have the CT. Are you following? So this means that every time I have to fine-tune something, I have to crash the car, get the, let's say we're having a robotics kind of a use case, crash the robot, let it terminate, then go back and see, all the returns, and then maybe I can perform better, crash it again, and so on and so on. So I have for several kind of use cases, which is associated with real world kind of problems. One thing is certain, it takes a long time to terminate sometimes. So in order to update the policy, it may, there's a inherent kind of latency there that you have to go. This means that your problem has to be slow moving. And then at the same time, it would be very expensive to implement something like that. And therefore, people started thinking something which, as it turns out, to be one of the, according to Sutton, probably the most important innovation in reinforcement learning across the whole range of algorithms. And this is why this specific algorithm, you will find it in many branches of reinforcement learning, including heavyweights like PPO, which people are migrating off from, or even inside GRPO. It's called temporal difference learning. And this is basically what we need to pay some attention to understand how the temporal difference learning ultimately is based on the belief that we have a Markovian system. So this is the ultimate connection, and this is why it's also ultimately connected to the Kalman networks. Although those connections are not going to be established. All right. In order to understand a little bit temporal difference learning, I am going to, or maybe I can present it first and then I can go to an example. I'll explain the zero in a few moments. TD, capital T, capital D. So we saw just now in Monte Carlo the update to be V pi with ST is equal to V pi with ST plus alpha GT minus V with ST. Those values. All right. So in a TD, we will see the following update. I'll write the update and then we'll explain. V pi ST is equal to V pi ST plus alpha RT plus 1 plus gamma V pi ST plus 1 minus ST. Everything here is capital letters. We are in a reinforcement learning space. That is TD 0. You may notice this term over here that took the place of GT. This term here is called the TD target. And effectively, this algorithm implements learn as I go. So let's try to understand what's really happening here. Let's assume, just to make an analogy, it's not a 100% valid analogy, but it is an analogy that you probably will remember after in an interview. Now, for me, the problem I'm facing every Friday, I'll tell you the problem I'm facing. I am in Brooklyn. I'm in state SB, right? And I have to choose from two actions. Okay. The first action is called the action A1, and the second action is action A2. A1 will take me through Brooklyn Bridge. Second action A2 will take me through the Manhattan Bridge. I will end, if I take the Brooklyn Bridge, I will arrive at in a S prime, a state. Let me call it S past Brooklyn Bridge, and the other one will be as past Manhattan Beach. So in a nutshell, this kind of algorithm will use what we call the bootstrapping to update the value of being in Brooklyn. So just like what happens with you many times that you're facing, maybe some of you are facing some kind of rough commuting situation, the moment you pass a landmark, which is supposed to be of certain value, right? Then you can update the value of being in Brooklyn in a sense. What you update is not the value of being in Brooklyn. It's, now it will take me just 30 minutes to reach my destination. Yeah. So that update is exactly what we do in TD learning. In other words, we will use the post landmark values as bootstrapping the value of Brooklyn. And therefore, updating also the value of being in Brooklyn, not only in terms of the value of being in Brooklyn, but also the value of the action that led us to the S prime state. Okay, and this also connects to something that we'll learn a bit later. You learn. So if you make this kind of analogy, I'm going to write certain things down now. So the so-called one-step. One-step TD of 0 combines the bootstrapping. The color is not accidental. Of dynamic programming, DP, and the sampling of Monte Carlo. In what sense? The equation looks almost identical to the Monte Carlo equation, except from the replacement of the sample return to go until the termination. So if I'm a state here, as in Monte Carlo, I was updating this value based on several trajectories, thousands of trajectories, based on the sample returns to go, 1, 2, 3, 1,000. Over here, I'm saying, I'm not going to wait until I terminate. I'm going to use this S prime state that has a value to update this value. If you watch the video, probably can see the camera, but this is basically what's happening with TD. If you arrive over there, you do the same with one step, TD of 0. Okay? We have not reached yet the generalization of TD of 0, but we need to understand first the TD of 0. Does this remind you something of associated with Markov? This is the reason why this TD target is borrowed from the MDP, which is called Markov decision process. Right? We are suggesting that the value of being here only depends on the value of being in the S prime via the bootstrapping established to us from the Bellman expectation equation. It doesn't get simpler than this. If you just spend 5-10 minutes thinking about the trajectories in this kind of room, and the example that I kind of gave you, that's the only way I think. Of course, there may be other YouTube videos as well you can watch, but that's the only way that you can understand what's happening. The Markovian assumption is actually there. This is the reason why when the TD algorithms deviate, face problems that are not Markovian, they don't perform very well. At least they perform suboptimal to algorithms that do not make this explicit assumption, like Markov chain, like Monte Carlo did not make any assumption. It just counted things and updated the state, the value of the state. Here we are making this assumption, this Markovian assumption. Hey, just give me the v pi of s plus 1. I will use this as an approximation to my future return. Effectively, that's basically what's happening. The v pi of s plus 1, why this is intuitive? Some other trajectories, right, were updated that value as v pi of st plus 1. Okay. There is a value. Use that to bootstrap using the Bellman expectation backup and update the value of being in Brooklyn. Any questions? This is the time to ask questions. So we can generalize this and in fact reach a point where this temporal difference will not be different under Monte Carlo. When instead of using just the next kind of state as plus 1, we wait and do the update over S double prime states that are coming after going, let's say, through the Manhattan Bridge, and S triple prime, and so on and so on. And at some point, using certain parameterization, we'll arrive at a construction where we have a parameter that, a knob, that when you tune it, you can vary the latency of the update. While in Monte Carlo, we had to experience the whole 100% of the latency until termination. Now we will be able to vary that kind of latency. This is called TD of lambda. Okay, it's very confusing initially, right? But it's kind of straightforward if you think a little bit about it. What we want to do now with the so-called TD of lambda is to decouple the function updates and the times functions are taken. In other words, let it act, let actions go, and then selectively I will choose, using this kind of lambda, how the updates will happen. Some kind of weighting, averaging is going to happen based on the expectation backups. Now, we're not doing just one state backup. We can do that over multiple states. So after n steps, let me write down the expression, it will become a bit easier. After n steps, Gt of n is equal to R t plus 1 plus gamma RT plus 2 plus dot 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 plus gamma n minus 1 RT plus n. I hope you recognize that, plus gamma to the power of n, V, capital V again. Now I'm going to put the pi on the top because I want to use the index for the specific subscript, t plus n minus 1 of st plus n. So you see what we are doing now. The expression is a bit more revealing. We are using the t plus n state as a proxy of the future return to go to do the backup. So we're not doing it. If you set the n is equal to 1, we are back to the previous situation. So our I want to write the general kind of expression now with any lambda, which is called a factor between, let's say, 0 and 1. We can parameterize this as g t of lambda is equal to 1 minus lambda summation from n is equal to 1 to infinity lambda to the power of n minus 1 gt of n. And I hope you recognize when the lambda is equal to 0, we are effectively obtaining TD of 0. When lambda is equal to 1, we are going to obtain the Monte Carlo update. The update in general is V t plus n first t is equal to t plus n minus 1 first t plus alpha gt of n minus vt plus n minus 1 first t. So I don't want to expand too much on the general kind of lambda. If you want to look at also all the details behind TD of lambda, although not for your final exam again, but my YouTube video goes through a little bit more details about this, right? And plugs in the various kind of values and shows what I just mentioned. What I want to do now, however, is to go through an example so that we can understand the difference between Monte Carlo and TD of lambda using just a very small example, and then it will be a bit more clear what's happening. So I am going to use the example which I have on the website. In fact, I think I updated this example today. And this is the example of this guy, MC versus TD of 0. This example is coming straight out of the Satans kind of book, and the notebook is matching the graphs that are there in the book using the Python code. So I advise you to take a look on the Python kind of side to understand, because in the Python, the update equations are kind of very straightforward. Like almost like, okay, if you are confused with TD of 0 and the update there in the Python, we will go through in a moment, they are very, very straightforward. But let me present first of all the problem, which is a very, very simple problem. So you see over here the problem. I will replicate the problem in terms of the graph that you see here with states and two terminating states. The states are A to E, and we have two terminating states on the left and on the right. You can actually see that only on the right, when you terminate on the right, only then you can get a reward of 1. Okay? All other rewards are 0. And over here we have a not explicit action. Whenever you are on the state, you have a probability of moving in other adjacent states, okay, automatically, until you terminate. So this is called Markov reward process, right? It's an example. Okay, so all episodes start from state C in the middle. All episodes start from state C. then proceed either left or right by one state on each step with equal probability. Episodes terminate after on an extreme left or an extreme right when, as I said, the reward is there. Okay, and so here you go. Let's write down this code of MRP example. The reason why we are going back to Markov decision kind of processes is that we can estimate clearly all expectations. Therefore, we can see exactly the value of every state, the exact solution of the state, and how the Monte Carlo approaches that exact solution. That's how you show that the Monte Carlo, with this kind of incremental update, the future returns is a good algorithm for the case where you terminate. And then you can also see how the TD of zero, what are the trade-offs between that and the Monte Carlo. We'll implement three algorithms here. So this is basically TL. This is A. This is B. This is C. D. E. E right. E right has reward of 1. All other rewards have 0. And we know the exact solution. We know the exact solution. We'll go to the website and pick the equation. Okay, so V pi of S. That's why you are writing notes, I hope, because some of these equations, you need to know them. I mean, you need to write them down. Okay, so summation over A, I of A given S, summation over R over S prime, E of S prime comma R given S comma A. I hope you remember all that. R plus gamma V pi of S prime. V is small letter. That is the Bellman expectation equation. That's the DP solution. All right, so we have assumptions. The problem assumption is pi of A given S. You read it, right? This is the skill of converting English into variables in the equations. Okay. 1/2 and 1/2. Left, right. That's one assumption that the text gave us. The other assumption the text gave us, gamma is equal to 1. Gamma is equal to 1. Or whatever number it doesn't mean. So now I'm asking you, just to test your understanding, what is V pi of A? V pi of A. What should I write here? Well, first of all, if you are in some form of facing a question like this, last week we asked you what is the V pi of S33. Yeah, that's what I asked you, right? And you were noting everything I was writing, in agreement, right? So now I'm asking you, what is the V pi of A? It's a much simpler problem, okay? So I think I remember me drawing some kind of tree, right? This is the S, this is the pi. I mean, it always kind of pays to do this just to understand what's happening. So V pi of A. So writing. Let's see. This is, I'm writing 1/2 of 0 plus V pi TL, okay, plus, okay, now you go. I cannot stand writing everything myself. Just you help me now. What should I write with after the plus? In the backup tree, are you going to put here A or something else? Yes, you're going to put there A. And what our future states are taking you from A? I mean, the future state could be TL. Is that correct? The future state after A could be TL. Okay, so TL is here. What other state you have? B. So TL and B. So now you go 1/2 again, right? Because you can go to either TL or B with equal probability. You can either go left or right with equal probability, correct? Are you seeing that, right? So okay, so some people are looking at what is this? It's nothing. I mean, honestly, it's nothing because you have the state diagram in front of you. You can either go left or right, and it cannot be simpler than this. Okay, it's 1/2 of 0 plus v pi of what? B. Which is equal to 1/2 v pi B. Because v pi of TL is 0. Without dragging it for too long, you can actually definitely calculate v pi of B in the same way. V pi of B will turn out. Basically, you need to tell me that you try this at home as you are reviewing dynamic programming. Don't look at the solution, just do it. Okay. Do you agree? Definitely V pi of A and C will show up inside that expression. So that's equation 1, that's equation 2. I'm going to write quickly the other ones. V pi of C is equal to V pi of B plus V pi of D divided by 2. That's equation 3. V pi of D is equal to V pi of C plus V pi of E divided by 2. That's equation 4. Finally, V pi of E is equal to V pi of D plus 1 divided by 2. That's equation 5. And now we have a system of that. This is exactly what we have done like, 3 weeks ago, whatever. System of linear equations we have, right? And we can solve it. But over here, the system of linear equations is so trivial that I have the V pi of A straight away. The V pi of A, I have the V pi of, anyway, let me write down the solution. V pi of A is equal to 1/6. V pi of B, it's 2 times V pi of A is 1/3. V pi of C, you tell me if you agree. V pi of C is 3 times the V pi of A. It's 1/2. V pi of D is equal to 2/3, and V pi of E is 5/6. You don't trust my arithmetic? Plug it in your ChatGPT and you will see. I mean, if you don't trust me, that's basically the solution. But Saturn also, before these systems got invented, definitely came up with the same solution. If we can see it, of course. This is the one. So came up with the same solution. Look. The true values is a dynamic programming solution. We had all the information we needed for this dynamic programming solution to be calculated in this very simple trivial problem. So this is a straight line, anything from 1/6 all the way to 5/6 as a function of the state. And now what we will do, we will go to Monte Carlo. First function, are you able to see the function? Generate episode. We are in the business now of generating episodes starting from a state that the problem told us. Okay. So start from C. Someone may ask you to write down some pseudocode during the final exam. Someone, I do not know, but try to make sure that honestly, I don't quote me on that because I have not developed the exam yet, but it's a very reasonable kind of pseudocode. While true, pick up an action, give us the next state, which is obviously deterministically here, given this, if you like, not deterministically, but with some kind of probability the action will reach that kind of state. Okay, and then actually, hold on a second. There's no state transition here, PSS prime, right? So the only thing is basically the probability of selecting an action. So it's deterministic, right? The PSS. Okay, so what we have here, we have the next state, and we create an episode. What is an episode? C, D, E, D, C, B, A, T, L. It's a valid episode. Each of these rewards will, of course, be all zero, right? But you have an episode. Your job after you have an episode is to understand, first of all, the MC prediction function, which is you start with some value function of everything is 0.5, right? All states have 0.5, right in the middle, in other words. And you go over the episodes that you generated, and look what happens here. Calculate GTs. Calculate the GTs from the state that you're in right now. Day to go. Do you see the line? G is equal to episode minus 1, 1. Yes.
Is it only the final reward?
The final reward is that at the end of the day, you're terminating. That's what matters. I mean, you have to tell that's what final is, termination.
It's still like accumulated over the trajectory though?
Yes, you will use the equation. I mean, you will use the equation, whatever the GT, right, equation I wrote, right? You will use the equation to calculate the discounted rewards that you got throughout an episode. But over here, it's everything is zero except from the terminating state. But of course, in a different problem, you have different returns. So you have V is equal to plus equal alpha, whatever alpha is 0.1. It's a scalar value, okay, typically small. G minus V of S. This is the update equation for Monte Carlo. Gamma is equal to 1. Okay, so the equations are trivial. So you will plot the Monte Carlo for alpha is equal to 1. Okay? This is basically your orange diagram for a number, of course, of episodes. Right? Whatever number of episodes this was created, I can't remember now. It was 10,000 episodes. You will be, obviously, it's an approximation. Obviously, it was an approximation. Okay, now, the same thing will actually happen with TD of 0 prediction. Again, for the same number of episodes and some value of alpha. Right here, the alpha is set to 0.01, but later on, I think I'm plotting as a function of alpha to see what's happening in the trade-off kind of discussion. You are generating the episodes, right? But look what's happening now with respect to the bootstrapping. Can you spot the bootstrapping line? Where is the bootstrapping line? Is the V next? The bootstrapping value, the V of S prime, is the V next. The V next, which is the value from the lookup, right? Whatever value it was there, you pick it of the episode t plus 1. Episode t plus 1 is where the episode led you. There's a value there, vt plus 1, v of s t plus 1. You discount it, and you add the reward, right? So you discount it and you add the reward. The r plus v next is your target, td of 0 target that I wrote in your notes. Are you following? Minus v of s. And you have your alpha there, and that's how you update again using the same sort of learn as you go equation, the v of s. Okay. And then finally, you are plotting again the TD of 0 for some value of alpha. I think they should have made the alphas consistent with each other, but I think the reason why we did it is that I think later on, when we plot the mean square error, what is the error here? The error is this difference. The error is this difference. The difference between the R, the bootstrap value, the R plus V next, minus the V of S. This is called the innovation, we called it, or residual, we called it in the Kalman filter. Again, we have the residual or called error in reinforcement learning terminology is between, back then it was the difference between the new measurement that is arriving, right, and the previous mean estimate. Okay? The previous mean estimate, the mean estimate, and the measurement, right? So it was the innovation. What new information the measurement is sending us in order for us to update to get a new mean back then, right? Similarly, we are doing this to update the values. So the mean square error, or the root mean square, is being plotted over here between Monte Carlo for various values of alpha and TD of 0. Okay. As you can see, TD of 0 is faster than Monte Carlo in terms of learning time. It's faster. As you can see, the algorithm kind of converges to some value earlier in terms of number of episodes. Okay. However, right, there is some kind of trade-off, right, in terms of bias and variance kind of trade-off. Now, because of the interest of time, I will let you process that kind of variance, and not for the final again, but you will see that the variance, right, is larger in the case of Monte Carlo at the expense of bias, benefit of the bias, right? It has smaller bias, but larger variance. And the TD of 0 has exactly the reverse kind of behavior. What I want to do now, right now, is to go back into the Monte Carlo control, okay? And in the because right now we just did evaluation, we didn't do anything. I mean, okay, we got our values. We can also expand this into Q values. Not only here, we saw the simpler V values, right, from pedagogical kind of reasons, but we can actually do the same thing with Q values. Okay, but still in the prediction kind of setting. Now we will see the control setting, which is basically the control stage, where it is equivalent to the value iteration and policy iteration we've seen in the MDP. Okay, here we will learn how to act optimally. Okay. Before we just did evaluation. So I'm going to cover a little bit model with the so-called model-free control range of algorithms. I want to describe what is called the generalized policy iteration, or GPI, which I think is a kind of kind of a visual that I want you to have in your mind, because if you remember, if you like the value iteration, avoided certain things that the policy iteration was doing, right, in order to get into a less expensive way of acting in the MDP kind of setting. And so we are going to be mirroring this kind of behavior. And the graph that I want you to have in your mind is this. So if I am to act optimally and I get a pi star and an associated q star, remember, still we are going to be getting something like that, right? Now these q's are written with kind of a small letters because you can do this in either MDP or reinforcement learning, okay? You will start with some kind of a Q value and a policy. And before we had to go this, before we were doing this, if you remember, that is what we were doing with, let's say, policy iteration, right? Now, I'm going to change the kind of a color a little bit. I can actually I don't need to reach all the way to the line where I have an exact kind of evaluation, and I can still converge. Okay, that was the premise. However, this is now even more approximate. In what sense? Let me write it down. With GPI, we generalize policy iteration to allow us take incomplete steps towards each goal run out of space. Another two terms that I think is worth kind of remembering, and this will actually guide you a little bit further exploration in this kind of domain, is the so-called on policy and off policy algorithms, right? That we are now getting in the control. Now that we are evaluating the control side and we are sort of studying that kind of acting kind of optimally, we want to establish in some instances, in many instances, some kind of decoupling between a policy that will guide the training data. Remember the training data we just saw a few moments ago in the Python notebook were the episodes, okay? And remember in this kind of a Python notebooks in the we were having all trained data coming from a policy. Now, if we are to update that kind of policy, we are in the so-called on policy space. We are creating trained data and updating the same policy. Okay? But in many instances, we are interested to decouple the two. In other words, we may explore and update a different policy than the exploration policy. And we'll see how that kind of is useful. But as a definition, I will define here the so-called on policy. The same policy transitioning the environment and learning how to validate the agent. In this case, we have the typical letter that we have. Then we call this policy pi. It's one policy. Okay. I'm creating kind of training data based on the returns that I'm seeing. I'm going to update the policy pi. Then after I update the policy, obviously after I update it, different training data will be generated out of this kind of policy. The off policy, we're going to have different policy to transition the environment. In other words, generate episodes, aka training data. This policy will be called behavioral policy. And we will symbolize it with mu. We also have policy that we act the target policy. Fine. This is the policy that we will be optimizing. In many instances, if we are facing, let's say, a deterministic kind of policy, right? We want still to understand what is out there, okay? And therefore, we are going to be able to trade off, in other words, this exploitation kind of trade-off that it is known in this type of algorithms. It's basically the flexibility of this off-policy kind of algorithms that will allow us. Maybe, for example, if my goal is general to exit the room, maybe there's another door that I do not know. And that is, this will allow me to sort of explore the environment a bit better. So there is, I will call it algorithms, which are in two broad categories: on-policy kind of algorithms and off-policy algorithms. The on-policy algorithm will be called SARSA, and the off-policy algorithm will be called Q-learning. Okay? And as it turns out, this will be the sort of algorithms that we will cover tonight. So this is what on earth is SARSA? It is based entirely on the TD prediction of the Q value. By the way, the name looks a bit strange, but it stands for state action, reward state action. Yeah, plenty of terms here. This is basically based on a TD estimation, the so-called prediction problem of Q of S comma A. And implements epsilon greedy policy improvement. So effectively what we have is we are connecting this A, we get a reward from this action, enter into state S prime. From that, we take another action called A prime, different than the potentially the other one. Obviously, this action has a Q value, S comma A, to remember what we were discussing. And this one is Q S prime, comma A prime. And if you remember the TD learning, right, was updating the value. I was using the V values as an example back then, right? But I told you the same thing can be expanded to two Q values. Was updating the value of this specific state based on a Markovian assumption about A. The best possible information we can get from all future states until we terminate is the value of ST plus 1. That was the Markovian assumption. Right? So imagine that happening now in the Q action value and for the Q action values. So we are using this bootstrapping again, and therefore no surprises of the kind of equation that I'm going to write here. I'll explain what epsilon greedy is. It's kind of pretty straightforward. So this is the Q ST comma AT is equal Q of ST comma AT plus alpha RT plus 1 plus gamma Q ST plus 1. I hope you remember what we call this guy. TD target. We called it TD target. This was the bootstrapping. Minus ST comma 80. So this is basically the update equation. So in terms of update equations, I think I try to be consistent. All of them are having this magenta kind of color. But one thing that I want to point out is that after the first stage of, let's say, of estimating this using the bootstrapping and doing TD learning, learn as I go, I need to act optimally. I need to adjust the policy after I learn after I update my Q. Now, because I have the Q, I can act greedily and pick up an action that gives me the largest Q, right? But I don't do that necessarily blindly all the time. This is basically where epsilon comes in. Okay. So epsilon is another kind of parameter that will allow us to flip a coin. And if the coin turns out which is bent with probability epsilon, and if the coin comes up to be heads, then I follow my greedy approach. But if it comes tails, out of all my possible set of actions, I do a random action. This allows me to do what? I'm not greedily acting all the time. I'm not beamforming, if you like, towards the door. I may go there, right? Or I may go back, and then repeat the process again. This means that I will explore, and this is basically the epsilon controls that kind of exploration exploitation. The trade-off. So I'm going to write this down. Okay. Continue. The algorithm will continue to estimate first comma A, and at the same time change the epsilon greedy algorithm. Don't say algorithm, just heuristic, I would say. pi. I am updating the same policy as I'm generating the data. That's an own policy. The fact that I'm not following what the policy is telling me is material. I'm not straight. I'm not generating training data out of a completely different policy. So this is basically the sort of SARSA kind of algorithm. And if you want, this is basically where my set of notes kind of end. I think I have learning, but I want to spend some time from the website on the Q learning. I'm sorry, I don't have handwritten notes for the Q learning, but the Q learning is an algorithm that is actually very similar, but it is actually an off policy control. It implements the off policy control. In other words, if you see the update equation over here, right, and you compare the SARSA update on the second line over here, look at the SARSA update we just wrote, and you see what's really happening on the Q learning, right? So it uses, if you like, the maximum over all possible actions. So effectively, this one will implement what's called the behavioral policy. So we have a behavioral policy which is the epsilon greedy in Q, right? And then we have a target policy where effectively we are going to be using the pi, right, the sort of target policy to pick up the so-called target. So the target changes, and because now we are effectively implementing the max over a prime, instead of using the pure bootstrapping the expectation. And then we are adjusting, if you like, the target policy, but we are effectively having two policies. So this is basically what the algorithm is. Yeah, I apologize. I don't have a lot of notes on the Q, but I do have the SARSA versus Q learning. So evidently something we didn't cover in the class won't be in scope for the final exam. So the value-based control, take it outside of the scope of the final exam to help you out a little bit, right? So, but definitely we covered up to prediction, I think, in an adequate kind of depth, okay, for reinforcement learning. So reinforcement learning will include prediction, and that will be it. But the cliff walking notebook is a famous example from the Sutton book that, again, in the future, you may want to go through to understand, again, using the Python code, again, how SARSA and Q-learning kind of differ and how they are providing different trajectories at the end of the day. This is a trajectory for SARSA and a trajectory for the Q-learning. SARSA, as you can see, because it steers away from this kind of I will call it a risky area that is associated with this red zone. This red zone, when you fall in, you go into because of the stochasticity of the environment, as you see in the example, you may go sideways, so you may fall into the red zone, and so SARSA is able to steer away from it because of this expectation calculation. It takes into account all of that, while Q-learning, it doesn't. It produces a better trajectory, but it's a risky trajectory. And because it is a risky trajectory, if you follow it, you will exhibit lower value overall across all episodes because you are falling into the pit. So if you understood that, it's doubtful you understood it why, but it is the material is there. Again, not for the final exam. Now, what we left on the table, I want to spend some time what we left on the table, okay, across the course. So you determine a little bit for the last a few minutes, your next steps, maybe the discussion will be useful. So let me title Left on the Table. Obviously, it is evident that reinforcement learning was not fully covered. One of the best things you can do is to, as I told you before, go slow, spend, let's say, probably something on the north of 3 to 4 weeks during the summer to finish reinforcement learning from the video lectures of David Silver. Okay, the video lectures are on YouTube. The links are on the website, and it goes through algorithms that we have not covered. The basic point where you deviate from the foundations to algorithms that are deployed today is reinforce, which is the policy gradient kind of method. We adapt straight away the policy. Okay. So many algorithms today for language models are based on that. Having said that, reinforce itself, as I said, is not only policy gradient. I mean, the modern algorithms contain both value-based schemes, right, and policy gradient kind of schemes together. And therefore, you require what we covered here and the reinforce. Okay, so the reinforcement learning finish David Silver's lectures in YouTube. Okay. That's one thing. The second is I told you that together with this Satos kind of book, there is a companion kind of book on written by Alphabet kind of engineers, a Pythonic book for reinforcement learning, also linked on your website. That book contains a good discussion on reinforce and also on proximal policy optimization. So out of that kind of, I always forget the title. It's like, which authors put some more memorable titles. Everything is titled Deep Reinforcement Learning something. Okay, but the link is on the website, on that beginning of the MDP introduction. So you will find it. So it covers reinforce in terms of Python and PPO. Now, GRPO is not covered there. So GRPO, you will cover it out of the DeepSeek's math reasoning paper. The paper should be listed because I'm going to be developing some material on that reasoning perspective. Should be listed in the website already. But that is basically will give you the difference between PPO and GRPO. The next thing, the next step for that is, I will call it, the next step for you should be looking at the various kind of notebooks under the reasoning chapter. Okay, so we didn't do anything about, we did logical reasoning kind of thing, but we didn't do anything about reasoning. The reason why we don't do reasoning is that you have to cover some algorithms in reinforcement learning and then go into reasoning, right, of language models. But the website, I'm covering some of that in more advanced courses myself. As of the fall, I will have the material kind of ready, but you can see under the book reasoning here, it's after reinforcement learning immediately. You can see this reasoning book is a must read, must watch video and a must read kind of notebook. This guy was in JP Morgan, and he since now he's a principal in Prime Intellect, which is one of the few companies. There are maybe 5, 6 companies acting in the space of reinforcement learning, creating environments for the Prime labs. So if they are in the business of creating environments, means that they are selling these environments. Or now they have also kind of platforms where everyone can go and test reinforcement learning algorithms on their environments, or they have communities where someone is uploading an environment, people are able to use it to benchmark their own kind of language models. So that business is kind of seems to be fruitful. But there are two, as I said, a few components on that kind of space. So it will apply GRPO on math reasoning using a small language model. So the small language model here is the Quen 2.5, 1.5 billion parameters. This notebook requires 55 gigabytes of VRAM to run. So you cannot run it in your own consumer hardware, but you can rent hardware from low-cost providers, but then the results are there. But it requires some hardware like that to run it. And you can run it also in Spark, despite the slowness of the machine. I'm talking about the DGX Spark, the little box from NVIDIA. This little box costs nowadays $4,000 or something. So you can also run it in NYU if you get access to some of the GPUs there. All right, so that's a must do after, just to understand for pure language. Obviously, you have also vision. So one other thing that we left on the table, apart from the reinforcement learning, so this is called GRPO and other notebooks on reasoning tasks. The other thing that we left kind of on the table is multimodal reasoning. I think after this class, if you get an A, that is, you can get very easily to understand multimodal reasoning. And therefore, during the summer, you may want to spend some time on understanding CLIP, contrastive self-supervised learning. So this is mean CLIP and Lava. These are two foundational kind of pieces of knowledge in terms of modeling that I think it will take you to a much better state that we are right now. These are things that are typically covered in computer vision, advanced computer vision classes. The discussion on both of them are on the website. The book that I'm teaching the computer vision class from, not in this university and another university, is free of charge. It's written by some MIT professors, and you can just see it on the web, both the CLIP chapter. There's no Lava chapter, but there's a CLIP chapter, very good written CLIP chapter there. All right, so that's a multimodal reasoning. You understand? After you go through multimodal reasoning, you go through these two from the MIT book. The MIT book covers only CLIP. Lava, you have to read the paper and also watch some other tutorials. There is a Lava notebook as well, I think, in my website. The next step for you is to combine multimodal reasoning and reinforcement learning. If you understand how reinforcement learning applies to language models, you can combine this with VLMs. So the next step is vision, VLMs. So Lava is a VLM. VLM plus RL. That's your next step. Then you start approaching and understand using, again, very simple small language models. In other words, you don't ever use large language models. Your aim here is to understand what's happening in the small domain. And then if you are applying reinforcement learning in the small domain, the benefits also will actually be amplified. Therefore, you get some kind of motivation out of it. And finally, the third step, which is, I think I mentioned that before, it's basically is AI engineering. This is where you you can actually read a couple of books in Safari, which I mentioned that in the past. So look at the Safari library. There is an excellent book called also AI engineering. I think it was something like that. Yeah, but I don't think I have. If you want, I can put it in Discord. If you're having, it's a best-selling book in Amazon. And the second is a book written by people who understand the latest GPU technologies. This is a very high demand skill. You understand how to build custom kernels, right, on NVIDIA GPUs, Blackwell and beyond. Blackwell and beyond. Anything below Blackwell is not useful. Blackwell, if you can get access to a Blackwell, that's why they're out of stock. You can actually get the significant benefit by looking at this book that teaches how to optimize in the specific GPU acceleration platform. So this is GPU skill, the GPU skill. Let me put it this way, GPU skill. If you master that, you can expand to edge GPUs, which are different than server kind of GPUs, right? And then this will give you some kind of touch point to other domains like IoT and robotics, more specifically. Robotics itself is another kind of area. You are not equipped right now to look at robotics before you take a classical robotics course. So you have to start from classical robotics. This means dynamics, kinematics, inverse kinematics. There must be a course like this in NYU that is doing that. If you are not able to get into a robotics course because of the oversubscription or whatever, there is specifically for manipulation. There is an excellent book called Modern Robotics. If you see on my robotics course, this is one of the books that I'm suggesting students to understand. Although my course is AI for robotics, which is different than classic robotics. The YouTube videos of modern robotics is there from the author itself. That's the best thing, and actually they are very well treated. And then, of course, after manipulation, then you actually start to understand some basics of manipulation, not everything. You can actually start, looking at AI plus robotics. In this kind of space, you need to understand world models. You need to understand fusion heads. So diffusion is something that I think I skipped in the in this diffusion. I'm not a very fan of techniques that are generating images just for the sake of generating images. However, the underlying principles of diffusion are used in robotics and other domains. So you have to understand the diffusion as a principle before you apply it over there. This is basically policy optimization approaches using diffusion heads. So that is basically the laundry list of so depending on your interest, you can pick a domain and you can work a little bit during the summer. Again, if you have any questions after the course ends, my door is always open. You can always ask questions in Discord, open a ticket, and I'm responsive during the summer. And I wish you all the best in the final exam. Although I'm sure no one will be able to talk to me after the final exam, or want to talk to me after the final exam. I wish you the best and good luck with your exams overall. Okay. Thank you. There are no